I am very excited for this. This is my first video, and as a first video, it's definitely going to have a lot of edits. If you notice any, just leave it alone, please. We're getting started with Unit 2 Forces. I figured we might as well get started with what we're working on. And these are just some of the things that's going to show up in the first video. And then as I start making more videos, I'll start the intro with more stuff on this screen, okay? So for video 1, we're going to learn about free body diagrams, net force, and a force equation, right? This is something that you can put on your yellow sheet. Free body diagrams always have an object, in this case like a box or a crate. All of these are just going to be very bland. So right now there's no forces acting on this object, so it's just staying still. But what happens when we have a force going straight down? When we have a force going straight down, it's going to start accelerating straight down. And when it starts accelerating, it starts moving like this. And notice it's speeding up as it goes down because it's accelerating. It's not just moving at a constant velocity, right? It's a force that's pulling it down. And it could be gravity, it could be, just a rope pulling it or something. You could be pushing it like that. But it's a force going this way. But what happens when we add another force that's not necessarily going in the same direction, or even in the other one where it might cancel, right? This one it's just all the way to the right. It's going in a completely different direction. So what happens? Well, in this case, you would add them up. And this is we're going to touch on this in a minute about net force, but this is the total force. Okay, this is not a new force, this is just the total force. And you can see, right, it lines up with both of them. Now, when this object is going to be set into motion, it'll start accelerating in this direction. And you can see here, right, it's accelerating down a lot faster than it is to the right because the downward part is bigger. It goes all this distance, but only this much sideways. And you can see, like, even if we turn this, it's still going in a straight line. Okay, it's still accelerating in exactly that direction, right? All right, moving on to net force, and this will explain kind of how those drawings work. And so from the last slide, we're going to bring this drawing with these two forces, okay? And we're going to kind of explain a little bit how we got that net force. So the net force is going to be like if you take all the forces acting on this object and put them all together into one, right? And when you do that, especially with vectors like this, right, you need to move them so that instead of starting at the same point, instead of starting in the middle of this object, they need to start at the end of each other. So like this one. Now, instead of coming out from the middle of this object, we have the net force going from the center to the end. Okay, and as we can see here, right, this is the y component of the net force, and this is the x component of the net force. But really, these x and y components were just their own forces just a second ago. Like here, they're separate forces, but now they're part of the same thing, right? They're just x and y components. And so you'll see net force here written a couple different ways. So one way you'll see it as net force, right, like this, or you might see it like this. And this symbol is a capital Greek letter sigma, and it's used a lot in math as representing sums or addition, right? So this kind of ties closer to the fact that you're adding these vectors, right? The net force is the sum of all these vectors, of all these forces. So it's the, instead of saying the net force, right, you could also say it's the sum of all the forces. But it's the same thing. It's the same force, it's the same vector, whatever you want to call it, right? It's just called a different thing, depending on how you look at it. So this is a pretty easy example because we have two vectors going in different directions and you just go from tip to tail and you're good, right? But now this one has three vectors, three different forces. And I drew So we got three different forces, and we're not going to label these forces or anything. They're just kind of generic forces, right? You could be pushing it this way or pulling it that way. But how do you find the net force when there's three different vectors going in all different directions? So how do you do that? Well, you start by moving around vectors tip to tail. So now instead of starting at the beginning here, you start at the end of this vector. And now what we're going to do with this one is we're going to move it over here. The total force, right, if you add all the vectors up, all the forces up, it goes right back to the center of mass, right back to the middle of this box. So this is an equilibrium, okay? The net force is 0. The summation of all the forces is 0. How do I know it's 0? Because it doesn't have any, there's no sum vector here, right? It's just right back to the middle. It's called an equilibrium when the net force or the sum of the forces is 0. So when all these forces equal 0, it's an equilibrium. It's not accelerating at all. So there you go. That's net force, right? You add all the vectors up. You add all the sum of the vectors, right? And then when they lead right back to where you started, that's an equilibrium. The net force is 0. Okay, they all balance each other out. And something to look at here is the x and y direction. We were using x and y on this side, but now on this one, right, the one straight down doesn't have any x. This one moves to the left a certain amount, but then this top one moves right back that certain amount. And no matter what this distance is, the x direction here, it cancels out with this one, right? And same with y. This one goes down, and you could say 5 newtons or whatever, and then this one goes up a little more than halfway, and then this last one kind of covers the distance, right? So the x and y components all cancel out, and they end up right back in the middle. Now, number 3, force equals mass times acceleration, right? You can put this in your yellow sheet or your pink sheet, whatever you have, and this is how you find the force, the mass, or the acceleration. Okay, you can use this equation for all 3. Now, I'm going to rewrite this with some massive gaps. And you may be wondering, what the heck are the gaps for? This is what the gaps were for. Okay, units, right? Force is in newtons, mass is kilograms, A is acceleration, meters per second squared. But newtons is its own unit, right? Kilograms times meters per second squared, nothing cancels, right? It's not like acceleration, where, you know, meters per second divided by seconds is meters per second squared. Like that just happens. But newtons, how do you get newtons from this? Well, guess what? Newtons is kilograms times meters per second squared. It's a compound unit. It's a shorthand, right? So instead of writing kilograms times meters per second squared, and it's a mouthful to say even, like every time you write newtons, you're saying this, just shorter. And it's really handy. So we go back to this box with the net force of 0. Well, if the force is 0 newtons, it can be any mass if it's not moving, it's not accelerating. Okay, so, you know, if it's not accelerating, then the net force is 0. Or if the net force is 0, it's not accelerating. Okay, so you can exert forces on it, you can accelerate it. Now let's go do some examples. Now we're going to start working through things. Okay, so let's say we have this box and the net force is down 20 newtons. So it could have a bunch of different forces that all add up to this, or just one. Whatever the case may be, its net force is 20 newtons straight down. Okay, and I know this is a little crooked, but it's okay. So we fill in, right? The net force is 20 newtons, so we fill this in right here. Now 20 newtons is mass times acceleration. We don't have either of those until I say 10 kilograms. Okay, this is nothing specific, it's just a generic example. If we have a 10 kilogram object with a net force of 20 newtons, what's its acceleration? Well, you can divide by 10 kilograms, right? This is being multiplied, so to get rid of multiplication, you divide. And when you divide 20 newtons, which is again kilograms times meters per second squared, and you take out the kilograms, you cancel it with this, now you have 20 over 10, 2 meters per second squared. But look what we just did, right? We took the force divided by the mass and got acceleration. Bam. Even though this looks like a separate equation, it's the same thing as this. All you had to do was cancel the mass with the force, right? But what if I don't know the mass, right? What if I just know the acceleration? So instead of acceleration force divided by mass, what if I'm trying to find mass and I have acceleration? Okay, if I have an unknown massive object, net force 20 newtons, accelerating pretty slowly, right, 1/2 meters per second squared, well, I can just do the same thing, right? 20 newtons divided by 0.5 meters per second squared, and dividing by 1/2, same thing as multiplying by 2, so 20 times 2 is 40 kilograms. Okay, and something to point out here is we watched a flipping physics video before we got started that was talking about inertial mass, which is its resistance to acceleration, and this is what it was talking about. So there are some finely tuned machines that exert a certain amount of force, say 20 newtons, right? And they measure that object's acceleration to find its mass. This is how it's done sometimes, okay? Sometimes you might use gravity, which is its gravitational mass, but it's the same thing, right? You have force, you have acceleration, and you divide it to find the mass. Rather than trying to, loosely define like how much matter is in an object. Okay, this is how mass is measured, not defined, right? And same thing here, right? We have net force divided by acceleration. We just went over this, right? So now I like to use this triangle, and I'll be honest, I use this just about every time we have a test like this on, when we're trying to find something other than just force, okay? Because it's easy when you have mass and acceleration, you just multiply them. But what this triangle does is it just gives you an easy way to say, okay, if I'm looking for force, I cover it up, and then what's left is mass times acceleration. If I'm looking for mass, I cover this up, and I have left is force over acceleration, which is what we have here. And same thing, cover up acceleration, and now we have force over mass. Okay, so that's kind of an easy way to remember what to do, and this is just the same equation. You just kind of move it around, right? All right, recap. Free body diagrams is when you have, an object with several forces, or maybe even just one. You just point out the forces that are acting on that object. Net force is when you add up all those forces, or the summation, or the sum of all the forces. And when that net force is 0, it's not accelerating, and that's when you're at an equilibrium. Okay, an equilibrium doesn't mean you're not moving, it means you're not accelerating. And another thing to look at is force is mass times acceleration. We just pointed out this triangle you can use, and you can just kind of draw this wherever. It's an easy way to remember what to do when you're trying to calculate each of these things, right? Force, mass, or acceleration, when you're given some of the others. All right, I think that was a pretty successful first video. I'm gonna have a lot of editing to do because that was rough. But yeah, keep coming back. Next time we're gonna start looking at these things, and it's gonna be interesting because we're gonna start doing more problems. This one was nice because, you know, here all we have to do is this, right? Just those little bit of problems was pretty easy. We could all kind of follow along with that. But next video, we're going to start moving into like actually doing problems. This was all just kind of foundational